All right, so again, we can do stoichiometry with gases, but often gases are measured by their volume, not necessarily grams or moles. So with gas stoichiometry, we'll probably see some data that might look like this. We are going to do a combustion. A sample of methane has a volume and temperature and pressure as given. It's mixed with a sample of oxygen gas having a volume and temperature and pressure as given. The mixture is ignited to form carbon dioxide and water. There's my combustion. Calculate the volume of carbon dioxide produced at a pressure of 2.50 atmospheres and a temperature of 125 degrees Celsius. Now, this does kind of make sense. The pressure has increased a little bit, and the temperature increased quite a bit. Well, check out what happens here. Let's say we write the balance equation. Methane is CH4. We're going to react it with oxygen, O2, to form carbon dioxide and water, usually in the vapor phase, because this is exothermic. So let's balance this sucker. How about 2 of these and 2 of these? Excellent. Okay, so we're starting out with 3 moles of particles, and we're forming 3 moles of particles. Now that's one thing that you can kind of look at in stoichiometry. If you form more particles than what you had on the reactant side in a closed container, your products are going to be at a greater pressure. There's just more particles in that closed container. Now this time we have the same amount of particles, but yet I notice that the final pressure is greater than the initial pressure of either reactant. Well, think about what happens in a combustion. Combustions are exothermic, and they're giving off a ton of heat energy, which is why the temperature goes up quite a bit. So if the temperature has increased, the particles have more kinetic energy. So even though I have the same number of particles formed on the product side, there are still 3 moles of gas. On the product side, these particles have more energy, which means more frequent collisions and more forceful collisions, creating more pressure. Interesting. Okay, so what do we want to know here? How much carbon dioxide is produced? What volume of carbon dioxide? Okay. We have 2 reactants, and I'm not really sure if there's a limiting or an excess, so we should probably check. All right, this is going to be fun. Let's start with methane, CH4. We're going to pervert this thing and solve it for moles so that I can check moles of each reactant and see if I have a limiting or excess, because that's going to affect the amount of carbon dioxide formed. So this is easy. Plug it in. Pervert. P, 1.65 atmospheres. V, 2.8 liters. I'm going to solve it for N moles. I'm going to use the gas constant in the AP packet in reference to atmospheres, and I'm not going to round it. 0.08206 atmosphere liter per mole Kelvin, which means my temperature does need to be in kelvins. So I'll add 273, make it 298. All right, let's plug this in and solve for N moles. Again, I'm not going to use the constant for my sig figs, so everything else looks like there are 3.01, or I should say 0.189 moles of CH4. All right. Now we're going to do the same thing with the oxygen. We're looking for a limiting or excess reactant. So let's do the same thing with oxygen. 1.25 atmospheres. The volume, holy man, 35.0 liters. I want moles. My gas constant is the same. 206. Atmosphere liter per mole Kelvin. And my temperature is 31 degrees or 304 Kelvin. Let's plug that in. It's all for moles. Holy moly. Okay, 1.75 moles of oxygen. Well, I think I answered my question. If there's a limiting and an excess, yeah, there is. The limiting excess thing, like, don't let that get your undies in a bundle. You look at the ratio from the balanced equation, and you can usually do this by inspection. I'm supposed to have twice as much oxygen in moles, twice as many moles of oxygen. So I compare what I have. I'm supposed to multiply that by 2. Yep, we got it. We got well over the needed amount of oxygen. So by far, oxygen is my excess reactant. And that leaves methane as my limiting reactant. Which, honestly, this makes sense. If you're doing a combustion, you're probably going to run out of your carbon compound. That's like your fuel before the atmosphere runs out of oxygen gas. I mean, your cars probably run out of gas before the atmosphere runs out of oxygen. So often in a combustion, oxygen is your excess. But I just wanted to check and make sure. And it is. Okay, so now we can really do some stoichiometry and figure out how much carbon dioxide should be formed. So I always compare my limiting reactant to my product. Let's get ourselves a little more. Whoa, not that much room. Come back here. There they are. Okay, so I want my limiting reactant. And I can start with it in moles already. Since I took the time to calculate moles, might as well use it. Okay, so that was all just to figure out the limiting reactant. Now here comes the good stuff. 0.189 moles of methane, my limiting reactant. We'll do a little stoichiometry. Oh, nice. Well, I'm going to put this down anyways. 1 mole of methane to 1 mole of carbon dioxide gives me 0.189 moles of CO2. Now you might be thinking, I knew that. Would I have had to show that work? Not necessarily, as long as you showed the balanced equation. If you showed the balanced equation, it would be understood that it's a 1-to-1 ratio between the methane and the carbon dioxide. You wouldn't necessarily need to show what I just did there, as long as you had the balanced equation. Okay, so now if this would have been at STP, standard temperature and pressure, I could just use that ratio, 22.4 liters per 1 mole of gas. It's not at standard temperature and pressure, so we have to do one more little calculation. This is going to be for the carbon dioxide. We got to do a Pervnert again. The final pressure is 2.5 atmospheres. We're looking for the volume of gas, but now we know moles. So it was 0.189 moles of CO2. We can use the same R value, 8206 atmosphere liter per mole Kelvin. And the final temperature in Kelvin would be 398. There, so we can plug this in and solve for the volume of carbon dioxide. With 3 sig figs, volume of CO2, how about 2.47 liters? Not bad, huh? So in general, you may end up using this Pervnert to solve for moles, and then the rest of this was really just a stoichiometry problem. And then at the end, to go back to volume, since it wasn't at standard temperature and pressure, our only option was to go back to Pervnert.